Today, we are diving deep into voice AI. And I don't mean just transcribing a single voice memo. We're talking about building systems that can listen to and understand thousands of live conversations all at once. It's a massive engineering challenge, and we're going to pull back the curtain on the architectural blueprint for how it's actually done.
So let's just get right to the big question, right? How in the world do you build a system that can handle thousands of simultaneous phone calls or live meetings and turn all that speech into text, not in a few minutes, but instantly and without failing? Well, that's the puzzle we're going to solve.
So here's our game plan. First, we'll get our heads around why this concurrency thing is such a unique challenge for voice AI. Then, we'll lay out the architecture that can handle the scale. And we'll break it down into 3 core pillars: making it fast, making it scale smart, and making sure it's absolutely reliable.
Okay, first things first, we have to understand the core of the problem. You see, handling thousands of real-time voice streams is a completely different beast than managing, say, a busy website. It's just a whole different ballgame.
And this really gets to the heart of it. Traditional web stuff, that's all about handling lots of short, separate requests. You know, someone clicks a link, gets a page, and that's it. But with voice AI, you're not dealing with quick hits. You're maintaining thousands of continuous, long-running connections for minutes, maybe even hours. It's a marathon for every single user, not a series of quick sprints.
Now, you might be thinking, hey, why not just grab a great open-source model like OpenAI's Whisper and call it a day? Well, the problem is the vanilla version just isn't built for this kind of marathon. For starters, it thinks in 30-second chunks, which is a total non-starter for a real-time conversation. On top of that, it's just not optimized for production. It's slow, inefficient, and sometimes it can even hallucinate text or just drop entire parts of the conversation. It's an amazing model, for sure, but it's not ready for primetime right out of the box.
So how do we fix this? Well, trying to build one giant monolithic application is just a recipe for disaster. I mean, think about it. One bug could bring the entire system down, and you couldn't scale up your transcription power without scaling everything else along with it, which is just crazy inefficient. The real answer lies in a much smarter design, moving from that clunky monolith to microservices.
And that brings us to microservices. The whole idea here is to break a huge, complex problem down into a bunch of smaller, independent, bite-sized pieces. Each service has exactly one job, and it does that one job really, really well. And the beauty of this is that we can upgrade, fix, or massively scale one piece of the system, like our transcription engine, without ever having to touch anything else.
Here's what that looks like in the real world for a voice AI. A conversation isn't just one thing, it's a pipeline of different jobs. You've got one service that just listens for someone to start talking. The next one does the heavy lifting of speech to text. Then another acts as the brain, figuring out what to do with that text. And finally, one generates a spoken response. Each one of these is its own separate, scalable microservice.
All right, let's talk about our first pillar. If you want to handle thousands of streams, your core engine, the part that actually does the transcription, has to be blindingly fast. We're not talking about a few software tweaks here. We're talking about fundamental optimizations. This is all about the need for speed.
And hey, don't just take my word for it. The team at Base 10 said it perfectly. Vanilla Whisper is just far from production quality. It's inefficient and it's slow. See, optimization isn't some optional, nice-to-have feature. It's the foundation. You just can't build a skyscraper on a foundation made of sand.
So how do we get this speed? Well, it comes down to a few key techniques. First is quantization. Think of it like using simpler numbers to do math, which makes everything way faster without really hurting accuracy. Second, we literally swap out the standard Python engine for a supercharged C++ one. And third, there's this really clever trick called in-flight batching, where you group little audio snippets together on the fly to make sure your super expensive GPUs are working at 100% capacity all the time.
And the results? They're pretty staggering. Just look at this. Use something like Faster Whisper, which uses that C++ engine we talked about, and boom, you're already 4 to 6 times faster. But then you bring in the heavy artillery, like NVIDIA's TensorRT-LLM, and you could be looking at a 20 times speed up over the original. It's a huge difference.
So at the end of the day, what are we talking about here? We're talking about a system that is, at a bare minimum, 10 times faster than what you get right out of the box. That is the kind of performance that actually makes real-time scale possible.
Okay, so we've got a really fast engine. That's great. But how do we manage our resources? We can't just have thousands of servers sitting around running 24/7. We'd go broke. And that brings us to pillar number 2, scaling smartly. And the key piece of tech for this is a tool called Kada.
It's an event-driven autoscaler for Kubernetes. Now, what that really means is it lets our system react to the actual work that needs to be done. So instead of just watching the CPU meter, it's watching the line of jobs waiting to be processed.
Now let's compare that to the old way of doing things. The standard Kubernetes scaler is reactive. It only adds more servers after the current ones are already overloaded. It's always playing catch-up. But Kata is proactive. It sees the line forming, it sees the work piling up, and it scales up before the system gets overwhelmed. It's just a much, much smarter way to operate. And right here, this is Kata's killer feature. This is the magic trick. When there are no calls coming in, like at 3 in the morning, Kata automatically scales the number of your expensive transcription servers all the way down to 0. You pay for absolutely nothing when it's idle. The second a call comes in, it spins everything back up instantly. It's a game changer for cost. Okay, we've got speed and we've got smart scaling. Our final pillar is all about reliability. How do we make sure all that audio data gets from point A to point B within our system without getting lost or corrupted, especially when things get crazy busy? It all comes down to the data transport layer. This analogy is just perfect. Think of your network like a highway. When that highway gets jammed up with traffic, cars get stuck, or in our case, data packets just get dropped. And for real-time audio, a dropped packet means a glitch, a stutter, a missed word. It's just completely unacceptable.
So we need to pick the right kind of car for our data highway. And the two main contenders are WebSockets and gRPC. Now, WebSockets are awesome for connecting the browsers, but for the communication between our internal services, gRPC is an absolute performance beast. It's just built for this stuff. It's super efficient, sends data in a compact binary format, and can handle tons of streams at once.
So the best solution isn't to pick one or the other. It's a hybrid approach. You use the right tool for the right job. We use WebSockets for that first connection from the user, because it works everywhere. But the moment that audio hits our system, everything zipping around between our services is happening over the much faster and more reliable gRPC.
And just look at the numbers. They really speak for themselves. Making that switch to gRPC for internal traffic can cut your latency by more than half, more than double your throughput, and slash your bandwidth needs by up to 80%. That isn't a small tweak. That is how you build a rock-solid, high-performance pipeline.
And there you have it. That's the whole shebang. When you put these 3 pillars together, a super optimized engine for speed, an event-driven autoscaler like Kata for scale, and a smart hybrid transport layer for reliability, you get the complete blueprint for building real-time voice AI that can handle pretty much anything you throw at it. So building an architecture like this opens up some incredible doors, but it also leads to a much bigger question. Now that we've figured out how to build this incredible digital ear that can listen to and understand the world's conversations in real time, what happens next? What does AI do with all that understanding? That's the next frontier. Thanks for tuning in.